Okay, we're ready for 11.2, permutations. Hopefully you did well on your homework for 11.1. You understood this counting principle, the multiplication principle is nice and clear and working in your mind because we're going to apply it here to something called a permutation. What is a permutation? Well, let's get started. So before we define what a permutation is, though, we're going to use in this thing the fundamental counting principle, the stuff we learned in 11.1. We're going to learn that there's something called a factorial expression, something with an exclamation point. So you may have seen these before, but it's a natural outflow of what we've been doing. We're also going to find that there are formulas for doing a permutation, and we're not going to worry about number 4, okay? Not in this lesson. So first of all, what is a permutation? It's simply an ordered arrangement. Isn't an arrangement ordered? Yeah, but it's just emphasizing order is important and things are in an arrangement. Okay, we'll see that in 11.3 we'll talk about certain types of groupings where order is not important. So we've got a club and how many members, and you're all members, you got sort of equal footing. That's not important. Permutations are, you've got an executive board, you've got a president, vice president, so forth. You've got sort of job duties, and each person has different authorities, different responsibilities. The order is important, depending upon which job you got. So we'll talk about those. But one of the things for a permutation that's important is no item is used more than once. So you can't be both president and secretary. Sorry, that's not possible with a permutation. And the order is important. It makes a difference. So like with the song list, you might think, oh, I've got 10 favorite songs. I don't care what order I listen to them. But when you put them in a playlist, they are in an order. First, second, third, fourth song. Ordering is important. Also, music has an emotional effect. So if you go from what should we say, light music to more emotionally charged music, you might get people motivated to get active, start dancing, something like that. You know, if you have any DJ friends, they know this exactly. Or you could do the opposite, start with the highly charged music, bring it down, and you can put people to sleep. So order makes an importance. Okay. So here's an example. We're going to take our 7 favorite books, and we're going to put them on a shelf. So how many different ways can we arrange that? So let's just think through this, how we would do that. So we've got 7 books. We need a bookshelf. We need 7 slots to put those 7 books. 1, 2, 3, 4, 5, 6, 7. So I carry my 7 books with me. Here they are. Maybe I should get real visual, but I'll sort of get visual over here. So when I come to this first slot, we'll call that the first slot. This is the second slot, the third, right? Because order is important. I've got how many choices? I have 7 different books I could choose to put here. I take my choice, boom, there's my book. That's the one I want to put there. So now, how many are left in my stack? Well, I've put 1 there, so I must still have 6 in my stack. So for the second slot, I've only got a choice of 6 books. I choose one. This one looks good. Nice little skinny one here. Here's my little skinny book. I'll put that one there. Boom. How many books do I have left? I've got 5 books left. Put a book. How many are left? 4. Put a book. This one. Let's go with this one. How many are left? 3. Put a book. How many are left? 2. How many are left? 1. I have no choices, but I have to put a book here. There's really 1 choice. Oops, I'll put it down here. It's 1. Okay, so 7 times 6 times 5 times 4 times 3 times 2 times 1 will give me the number of different arrangements I could have done. Because I could have chose this book at the front. I could have put it in the middle. So all the different ways I have of organizing, just take 7 times 6 times 5 times 4 times 3 times 2 times 1. It's a big number, I know, so we're going to let them do it. Here they've done it for us, but they just sort of did it. Um, and they kind of walk us through it. See, once you choose one, you've got 6 choices for the second position, so forth and so on. So 5,040. And we're going to see in the next slide, this is also referred to as 7 factorial. If you've got a calculator that has a factorial key, that's what it does. It takes 7 times 6 times 5 times 4 times 3 times 2 times 1 and gives us 5,040. Okay. So here it is in printed letters, 7 factorial, written 7 exclamation point, and simply read, it's that operation takes whatever number you put there, and they call it in to generalize it, some integer in. In could be 7, it could be 17, it could be 146, it could be any integer. And the way it works is, let's say this is 15. 15 factorial, what is it going to be? 15, and then 15 minus 1, that's 14. 15 minus 2, that's 13. Dot, dot, dot. You would keep doing that all the way down, and you always get 3 times 2 times 1. So it's from 15 all the way down to 1. We multiply all the numbers together, and that's what a factorial is. Now, simple definition is, you would think, yeah, 1 factorial, that's 1, just 1. 1 times what? I don't know, 1 is 1. But the other thing is, by definition, they make 0 factorial also 1. But let's think of the difference. 1 factorial represents I've got 1 book, so I've got 1 thing to put there. There's 1 arrangement. If I had no books, I still have 1 thing I can do, which is nothing, right? I can't do anything else. So the idea of 0 factorial is I got nothing, so I can do nothing, but that's still 1 thing. Okay. Don't think about it too deeply, because that'll get you confused. So just know that if you got 0 factorial, we're going to look at this later, probably when it comes up. That's actually 1. It is not 0. If you make it 0, the world falls apart. So we don't want to do that. And it's not accurate. If I got nothing, I can do nothing, which is 1 thing. In fact, nothing is my favorite thing to do a lot of times, although lately we're just sitting home doing nothing, so we would like something to do. Okay, so now here's a few examples. So here's 8 factorial over 5 factorial divided by 5 factorial. So how could we do this? Well, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. Notice this is all multiplication. So 5 divided by 5 is 1, 4 divided by 4 is 1, 3 divided by 3 is 1, 2 divided by 2 is 1, 1 divided by 1 is 1. So we are left with 8 times 7 times 6. Okay. And what I'm going to show you is that this is an example if we had 8 books but only 3 slots, right? Let's think back to while we were doing things. I've only got 3 bookshelves, 3 slots for 3 books, but I've got 8 favorite books. What can I do? Well, I have 8 choices for this first slot. Now I've got 7 books left, so I've got my 7 favorite. I choose 1 there. Boom, I've got 6 left. And then what I do, I put the other 5 off somewhere so later I can bring them out, because I don't have any room to put those other books. So what I get is 8 times 7 times 6, 336. I have 336 arrangements of those 8 books, chosen 3 at a time. Okay, so that's the kind of permutations we're going to be dealing with. Okay. Be great if I had room for all 8, because they're all my favorites, right? But I only got room for 3 at a time. Small apartment. Okay. Now let's watch. If we've got 26 factorial, do you really want to write 26 all the way down to 1? I don't. So watch what we're going to do. We're going to say this 21 factorial, I'm going to write that down first. I can stop when I get to 21. So I go 26, 25, 24, 23, 22, 21, and the rest go down. So I'm just going to call that 21 factorial. These folks are going to cancel each other out. They divided it, they're the same thing, so they divide out. So what this ends up being is this would be 26 things, and 1, 2, 3, 4, 5. I've only got 5 slots left, so this is another type of a permutation type case. It's a much larger case, obviously. 7 1,893,600 when we multiply this out. But it's a lot easier than trying to multiply this and then divide by this. What happens is these numbers become so large if you don't use some of these formulas and such in the abstractions, your calculator will actually overflow. It won't be able to make the calculations. So this is what we're going to use for permutations. And again, I've been showing you a system where we don't really need this formula, but I'm going to show you how it's connected to the formula. So let's go back to our 7 books, chosen 3 at a time. So that's a permutation of 7 items that we choose 3 at a time. The way I would do this, and the way I do this, is I see the 3. That's 1, 2, 3 slots. The 7 is how many I have to choose from, so I can 7 for the first slot, put 1 there. 6 for the second slot, put 1 there. 5 for the third slot, and then the rest goes somewhere else. But that's what 7 permutate 3 is going to be. Now let's see, using this formula, that we will actually end up with the same thing, but it kind of takes a little bit longer. When we did it this way, we were thinking that we had 7 items and we're placing 3 of them. We understood what we're doing. When we come over here, we get into the abstract and we might lose track of what we're doing. So this formula says just take n factorial. So again, we're going to say that n equals 7, r equals 3. Okay, so that is 7 permutate 3. Okay, 7 permutate 3. So that gives us from the formula 7 factorial. N is 7, r is 3, so that's 7 minus 3 factorial. Well, what's 7 minus 3? 7 minus 3 is 4. So it becomes 4 factorial. And now remember what we did last time. We go to 4 factorial in the bottom. We're going to write from the 7, so we're going to start at 7. We're going to stop at 4 factorial. So we do 7, 6, 5, 4. Oh, we get to stop. The 4 factorials cancel. Look at, we got exactly what we got over here, but it took us 1, 2, 3 steps to get there. Okay, the calculation will be the same, but you choose your way. Here's a Little Crow's method that I figured out this after doing a lot of these, and I go, man, that's a lot of work. Wait, I could just go this way, and I understand what I'm doing a lot better. Okay, so here's one. I apologize that this was supposed to show up later, but you and 19 of your friends, so that's 20 people, right? We're going to have a business. We need 3 officers. And again, order is important here because there's different job duties. There's a treasurer, operating manager, and CEO. So how many different ways can we choose this? Again, choosing different people. In my experience, if you have 20 people, you're going to have just really fewer people to really choose from. There'll be some people that are just kind of joined the business for whatever reason. But let's just say we're all the folks that you have are very well qualified. Maybe it's going to be randomly assigned. But anyway, the way, because any one of them could be CEO, any one of them could be operating manager. So again, what I would do, we've got 3 offices, CEO, operations manager, and treasurer. CEO. How many people can we choose for the CEO? Well, we got 20 of them. Once we choose a CEO, that CEO cannot also be operating manager. That would not be cool. So there's only 19 people that could fill that role. How many people could be the treasurer? Well, we only got 18 people to choose from now. There we are, 20 times 18 times 18. And what you see, that's using the permutation formula. That's exactly what happened. We end up 20 minus 3 is 17 factorial. That part canceled out. Here it is right there. But we went straight to the heart of the problem. And I think you're going to understand the problems better this way as well. Okay. We do want to see how the formulas work for later, maybe. But I believe it'll come when you need it. But what you need is the understanding first. So this is the middle thing. Yeah, R is 3, N is equal to 20, and the order met. It's a difference because the responsibilities are different. That's it. That's it. Like I said, that's all a permutation is. So what I'm going to ask you to do now is, because I need a little break, I would like you to go work on some homework 11.2. Work through those problems of doing some permutations. Choose your method. Maybe use both of them. Use the formula. Use Little Crow's little counting method. That's all I use is the counting method. Uh, but it's because I did have experience with the formula, so I know how to use it. You also have those formulas on your calculator if you've got a TI-84. In fact, why don't, since I'm here, well, I tell you what, when we're done with 11.3, I'll show you how to use the calculator because I want you some practice doing it by hand. Okay, work hard and we'll see you in a flip of a switch back at 11.3. Thanks.